Today we're going to speak about black hole uniqueness theorems. We are interested in stationary solutions as the endpoints of the gravitational collapse, and from the previous lectures we have seen that black holes are the generic endpoints, because we have seen that singularity is a general feature from the Penrose singularity theorem, as well as we saw that horizons also must form. Partially, so on the one hand, from the cosmic censorship principles that should hide the singularity, and on the other hand, by the Lichnerovich theorem introduced in last lecture, which says that globally stationary spacetimes must necessarily be Minkowski. The question is then, can we classify the endpoints of the collapse, the stationary black holes? And we give the positive answer, yes, we can. The Kerr black hole is the unique stationary black hole under a number of assumptions. So, this theorem, so in the theorem on the screen, I have merged two theorems by Carter and Robinson and by Hawking and Wald together. So if you take a stationary asymptotically flat spacetime, which is analytic solution of Einstein equations and sufficiently regular around the event horizon, then this solution of Einstein equations is isomorphic to a Kerr solution. So this theorem in four dimensions naturally holds for the presence of a Maxwell field, as well as there are generalizations for the presence of a neutral scalar. However, it notoriously breaks down for the Young Maxwell field because of the complicated group structure. It also breaks in the presence of a complex scalars, where we start getting what is called complex hair. And the most problematic case is the case of a non-zero cosmological constant. We will touch briefly on this subject in this lecture, but the main problem is that the presence of a cosmological constant sufficiently breaks some part of the solution process of the Einstein equations, and we can neither derive a similar statement, a similar theorem, nor we can disprove by actually finding another family of black holes similar to Kerr ADS solution. So the strategy of this proof consists of two big steps. So essentially, the Einstein equations must be seen as a boundary problem, where we specify the boundary conditions on the event horizon. So first of all, we must geometrize the event horizon. We must introduce a chart around the event horizon and see how the fields, well, the metric behaves around it. And then we must do something with the Einstein equations. Fortunately, in the absence of a cosmological constant, the Einstein equations possess a very remarkable property for stationary and axisymmetric solutions. More on this later. So, let us start with step one. Let us see how the geometry behaves around a stationary event horizon. So, let us start with an important definition, a definition of a killing horizon. So we will call a null hypersurface N to be a killing horizon if there exists such a killing vector field, in the neighborhood of this null hypersurface, which is normal to N. So, our main statement for today would be the rigidity theorem, proved by Hawking, which gives two important consequences. So the first one is that can be summarized in that a stationary event horizon must be a killing horizon. And the second one is that this killing horizon is a special one in the sense that stationarity, under certain further assumptions, implies the existence of another symmetry, the axis symmetry. So let us start the sketch of the proof. First of all, let us recall a number of results from the section about causal structure. So, observe that the event horizon is necessarily a null hypersurface. So, an event horizon without assumption of stationarity, so including dynamical scenarios. So first of all, firstly, recall the definition of the future event horizon as being the boundary of the causal past of the future null infinity. So the boundary of the region from which we can send a light signal to infinity. Of course, this must be intersected with M, because we have been defining the scribe plus with respect to non-physical space-time, if you recall the lecture on the asymptotic flatness. But this is a deal here. So we have given this definition for the asymptotically flat case. Similar results would hold for the asymptotically ADS scenarios and asymptotically DC scenarios as well. So there, similar statements, similar definitions for the event horizon would hold. But we will fix on the asymptotically flat case. So, secondly, from the lecture on the causal structure, we recall that the boundary of the causal past of any subregion of the space-time is an achronal submanifold of the space-time. And what does achronal mean? Achronal mean that any 2 points lying in this submanifold cannot be connected by a time-like curve. So, in other words, the tangent space, the tangent bundle to the submanifold does not contain time-like vectors. So this hypersurface is either null or space-like. Now, we'll show that this is null. So recall the following theorem from Wold. Recall the following theorem from the same lecture, the theorem by Wold. So we have called it, we have numbered it to be theorem 2. So any point of the boundary of the causal past of closed U lies on a null geodesic going through, lies on a null geodesic which lies entirely in this boundary. So In other words, every connected component of the horizon, in case we can have multiple black holes, is indeed a null hypersurface. Good. So, indeed, any event horizon is a null hypersurface. Now, let us bring the Killing vector fields onto the stage. So, the first statement we want to prove is that given any Killing vector field, the event horizon must be preserved under it. So, H plus is by all so let's do the proof by contradiction. So first of all, we expect that so the event horizon was defined topologically as the boundary between the two regions, accessible and inaccessible from the infinity. And we expect that since it's a topological property, it must stay invariant under the isometries of the space-time, which are generated by the Killing vector fields. So, proved by contradiction. Let us assume the opposite. So let us have an event horizon, and we have a point Q on it, and let the horizon to not be preserved by the Killing vector field. So what does it mean? It means that the orbit of the Killing vector field, the orbit of this isometry, leaves the horizon. So let's say we have an orbit of the Killing vector field passing through the point Q, and the orbit would then go as this. So if it takes, so it means that since isometries are of course continuous, we're working with a continuous space-time, we can take a point P outside the event horizon, which is sufficiently close to it. So outside the black hole. So what does it mean? Since P is outside of the black hole, we can construct a time-like curve, a time-like geodesic, which goes to infinity. So now, the geodesic equation is generated by the metric, and therefore it is invariant under the isometries of the spacetime. So, in other words, there will be a similar time-like curve for any point on the orbit through the point P, including for the point Q on the horizon. So, there is such a curve for Q as well. this is, of course, a contradiction. We cannot leave the black hole region. We cannot leave the event horizon. So now, let us recall the Gaussian null coordinates. So recall that the metric on the null hypersurface is given by the following combination. Where geometrically it meant that if this is the null hypersurface N, the null generators are lines within N. So the coordinate, so the null generators U are given by G over G lambda. Lambda is an affine parameter along them. And Y are the coordinates on the spatial cross-section of N. So, for example, if you speak about event horizon for Schwarzschild black hole, they would be the coordinates on the two-sphere. And R is the coordinate of the event horizon. So this is D. So the vector in that direction is D over dr. And R is a fine parameter along the geodesics of D over dr. And the null hypersurface corresponds to R equals 0. So the geometry of spatial cross-section effectively, so if you treat the null hypersurface as a geodesic congruence, going through the spatial cross-section, then, well, the spatial cross-section necessarily, essentially gives us the geometric properties of it. I mean, the expansion, the shear, well, rotation vanishes, if you recall it. So gives us expansion and shear. For the congruence, of U through S, the spatial cross-section. So, for example, we have shown that the expansion gives us the evolution of the area of the spatial cross-section. So we have derived that the expansion theta is 1/2 of the d of t lambda of the logarithm determinant hij. So, similarly, the shear would correspond to the deformations of hij, which leave the area of the HIJ invariant. So theta measures the growth of the area of the spatial cross-section. So if theta is positive, the spatial cross-section increases. If it's negative, it shrinks. And in this construction, we have taken the vector u, the generator of this of the null hypersurface, and the vector of discongruence, to be future directed. So in other words, in our time-orientable space-time, and our space-time is time-orientable because we work with asymptotically flat spacetimes, and for asymptotic observers, we have our own notion of a space-time. Then we have our own notion of the time direction. Then it means that if theta is positive, the spatial cross-section of event horizon would increase with respect to asymptotic observer as well. Now, it is easy to see that the area of the event horizon should not shrink. So I'll leave it as an exercise, and you can check it in the 1971 paper by Hawking, that the horizon area does not shrink. So again, this is a statement for any kind of event horizon. We are not yet assuming stationarity here. If we further assume that our spacetime is stationary, that is, we concede that the endpoints of the gravitational collapse, Hawking managed to prove the further statement. So if we assume existence of a stationary kilometer field, stationary with respect to asymptotic observer. Of course, on the horizon it can be space-like or null. Then he managed to show that the expansion must be exactly 0, and the shear must be 0 as well. Then theta equals sigma equals 0, where sigma is the shear. So in other words, the horizon, in a stationary space-time, the horizon does not change with time. That is the null generator of the horizon, the killing vector field. The vector field u is a killing vector field on the horizon itself. And in more geometric terms, Hij on the horizon does not depend on lambda. So we have just proved that the event horizon is a null hypersurface which is preserved by all Killing vector fields of the spacetime, and in particular the null generator of the event horizon is a Killing vector field on the event horizon. Now, we have two options here. So, the first one is that the stationary Killing vector field coincides with the generator. So, the generator d over d lambda is the stationary Killing vector field. So then we immediately get that the horizon is a Killing horizon. So we also get that the horizon is not rotating with respect to the asymptotically flat with respect to the asymptotic observer, because if you recall, the rotation of a horizon, which we saw for the Kerr black hole, was the difference between the generator of the horizon and the asymptotic stationary Killing vector field. So the horizon is not rotating. And then, starting off the horizon, we show that the stationary Killing vector field is hypersurface orthogonal. Well, because it is hypersurface orthogonal to the event horizon. And then one can show step by step that it is hypersurface orthogonal everywhere. In other words, one can show that the full solution is static. So this was shown by Carter in '69. So the asymptotically flat solution is then static. And by this time, for the static by this time, the static spacetimes, the static solutions of the Einstein equations with a static event horizon were already classified. Israel and Bunting and Massoud have shown that the spacetime is necessarily spherically symmetric. So we end with Schwarzschild black hole, or respectively a Reisner-Nernstrom black hole if we include charged matter. So Israel, '69, which was later refined by Bunting and Massoud. In 1987. Asymptotically flat plus regular on horizon plus static means spherically symmetric. means Schwarzschild. Now, let us consider the second option. So, let our two independent vector fields. So, in other words, we have two killing vector fields living on the event horizon. They commute, and we can consider their orbits independently. Now, since d over d lambda is null, k must necessarily be space-like. So we have a space-like isometry on the event horizon, and one can rearrange these killing vector fields. One can take such a combination that k has closed 2π periodic orbits. In other words, k generates an axis symmetry. So, I mean, if k is null, so it's easy to show that k is space-like. We can consider the case of null k and just show by contradiction, because if k is null independent from d over d lambda, then it's necessarily d over dr, and then our geometry is strange. It means that all our space-time is essentially the infinite copies of the event horizon, which is unphysical. So k must be space-like, and it means must have closed space-like orbits. Closed because, well, the spatial cross-section of the event horizon is closed. We are not considering solutions which are like black strings or black planes. We are considering more classical black holes. For example, in 4 dimensions, the geometry of the event horizon, of the spatial cross-section of the event horizon, is that of a 2-dimensional sphere. So we can rearrange for some constant c. Orbits S1, 2π periodic. So, in other words, we have an axis symmetry on the event horizon. Now, we need the Einstein equations, the equations of motion, to progress further. And that's what Hawking does in 1973. So, he does series expansions of Einstein equations, series expansions of Einstein equations. So basically we are doing a perturbative solution of them. Einstein equations starting of the event horizon. So in the leading order, he finds the leading order of the near horizon geometry, which we can then take as the boundary conditions for our boundary problem. So next, okay. So we will write these these boundary conditions a bit later, and it turns out that these boundary conditions are that of a Kerr geometry. Next, Hawking manages to show, by doing series expansions to all orders, that d over d lambda is the Killing vector field to all orders. So it's a Killing vector field of the event horizon. So d over d lambda of hij equals 0 to all orders. And the same for other components of the metric. So d over d lambda is a Killing vector field everywhere. Hence, we have two Killing vector fields everywhere in the spacetime, and we can recombine them such that we have a stationary Killing vector field k, and we have an axis symmetry given by the combination of d over d lambda and k. Good. So, yes, and since d over d lambda is a Killing vector field, then indeed the event horizon, the stationary event horizon, is a Killing horizon. So, okay. So we summarize our result in the following theorem. So let our spacetime to be a stationary asymptotically flat analytic solution of Einstein equations with a non-extremal event horizon. Then it is either static or axisymmetric. This theorem was proved in a weaker form by Hawking and was later refined and strengthened by Crucial in 1991. So this theorem necessarily has a number of very big and very deep nuances. So, okay. So first of all, the theorem also works well with the presence of an electromagnetic field. So we just consider Einstein-Maxwell equations, and we also assume that the Maxwell field is also stationary. Okay. Okay. Now to the important nuances. First of all, it is analyticity. So this is a rather problematic assumption, because what does analyticity mean? So what is the difference? So analyticity means that the spacetime metric is an analytic function in some smooth chart covering the event horizon, for example in the Gaussian null coordinates. Analytic function, if you recall from calculus, it's a function entirely specified by behavior at a single point. So if we know the series expansions of a function at one point, then we know the function everywhere. Whether this assumption is physical depends largely on the field of gravity you're working with. So, to start with, this property that by knowing a function at one point, we know it everywhere, it's definitely a teleological property. So, sometimes, when we consider black holes to be simply mathematical models for something, we are perfectly fine with it. So, if you're interested in some qualitative features, or we treat black holes as mathematical models, as some laboratories, for example in a holographic setting, then we are perfectly fine to go. Secondly, if you go for numerics, we are sort of safe. Sort of. So, let us think of the difference between analytic and smooth functions. Because, well, because smooth is definitely a more physical assumption. We expect that the geometry, at least on the classical level, must be smooth. So, smooth means that all derivatives up to the infinite derivative of a function are well defined. So, the difference between the class of smooth and analytic functions are in the existence of functions with a compact support, that is the bump functions. A stereotypical example, so the stereotypical example of the so-called bump functions is the function f of x equals e to the power of minus 1 minus x squared, when x squared is less than 1, 0 if x squared is greater or equal than 1. So, it's an exercise to show that such function will be smooth everywhere, including at the point x squared equals 1. You can simply compute derivatives to all orders and find that they are smooth. So the plot of this function is exactly 0. Then it starts rising, it goes the hill, and then it goes down, and then it's exactly 0. So this is a typical function with a compact support. In mathematical physics, they rarely appear in the discussion, but sometimes they do appear. For example, in hydrodynamics, such exponential fall of tails can appear in the asymptotic analysis of certain solutions. So it's up to you whether to take it seriously or not. So if you bring in another level of rigor, so for example the mathematical GR people who consider the stability properties of black holes, for example that work I mentioned on the stability of the Schwarzschild black hole solution, then of course they prefer to work with as weak regular properties as possible, because we want to show the stability of the black hole with respect to all behaviors, including extremal ones. For example, the shock wave, for example, the stability under oncoming shock waves, and or possibly other defects. Finally, this assumption can be traded off for other assumptions. So in 2009, Kleinerman with his group has shown that has traded off analyticity for the asymptotical flatness. So of course, if you consider asymptotically flat four-dimensional spacetimes, we are safe. However, his proof essentially crucially uses asymptotical flatness and four-dimensionality of the spacetime. So therefore, it's poorly generalized. It's poorly generalized to other settings. So Kleinerman has lifted assumption for yes, his technique of proof does not work in high dimensions and does not work for non-asymptotically flat spacetimes. Okay, so the second nuance that is important to bring up is the assumption of a non-extremal event horizon. So let us recall what we mean by an extremal horizon. We saw such horizons for charged black holes and for Kerr black holes. So let Xi be the generator, of the event horizon. And of course, on every event horizon, Xi is necessarily null. So its norm is null. For the extremal horizons, however, the gradient of the norm is also null, is also 0. Which is a very it's also 0, which is a very serious complication. So the reason is that it breaks the procedure of perturbative solution of Einstein equations. So if you just assume it and plug what we have and plug our assumptions into the Einstein equations, well, at the leading order, we would get, at the leading order, we would get the leading order. However, at the subleading order, our procedure breaks down. Well, because for the extremal black holes, the extremal horizon appears as an infinite throat, basically separated from the rest of the spacetime. In fact, if you take the near horizon limit, the near horizon geometry, the leading order, would be a solution of Einstein equations itself, as we have seen for the Schwarzschild solution, where the geometry around horizon was the Robinson-Bertuzzi metric. And therefore, at the leading order, we will not be able to find all functions, to find all metric functions. In fact, we'll find a lot of freedom there. We would find an infinite group of near horizon symmetries acting on the subleading order, So effectively, we have a group of supertranslations acting on a near horizon data. There are attempts to lift this assumption, but the boost precise statement, which was done by Hollands and Nishibashi, so Hollands, Ishibashi in the same year, 2009, is that if you consider the modular space of all near horizon geometries, the because for example for the Kerr black hole, the leading order of the geometry will have two parameters, mass and the angular momentum. And for extremal black holes, it will have only one parameter because mass and angular momentum would be equal. So space of all near horizon geometries. Then the set of all geometries for which it can break for which rigidity theorem may fail is a set of measure zero. So in other words, for the generic values of mass or angular momentum, which is the same for extremal black holes, the rigidity theorem must hold. However, for some finite values that appeared as some roots of some algebraic polynomial, the rigidity theorem may fail. There may be some hairy solutions generalizing the Kerr family. However, none of them were found, so this assumption remains open as of yet. Lastly, if we agree on the analyticity and on the non-extremal event horizon, then all other assumptions are well generalized to other settings. So they can be generalized for non-asymptotically flat spacetimes. So they work well for lambda, for the presence of the cosmological constant. They work well in higher dimensions. They work well with various matter. And they even work well with the modifications of gravity. So, for example, if you treat Einstein gravity as an effective field theory, and we start adding higher order curvature corrections, that is squared in the rich tensor, squared, cubic, and so on, for these theories, the rigidity theorem will hold. So this was shown very recently in this was actually shown very recently in a paper by Hollands and Ishibashi and by Real. Hollands, Ishibashi, Real in 2022. So I promised you the Kerr geometry at the leading order around the horizon, and here it is. So it depends on the two parameters, the mass and the mass m, and the angular momentum per the unit mass a. So so it is an exercise to take the extremal limit. So take the extremal limit, which is given by the vanishing of the gradient of the null generator on the horizon. That is for the vanishing of kappa, which happens for I equals plus minus a. We can take plus because minus a would correspond to the opposite direction of the rotation, and check that it satisfies Einstein equations. This is easily done with the help of some mathematical package. For example, Wolfram Mathematica or Maple.